This is C++ code for implementing segment tree, and the code is from KACTL. So they are a code book for use in ICPC contests. So I added some additional comments. So in this in this code we have a class, a struct called tree, and it can be customized for a particular application. So there are four things that can be customized. One of them is what is the base data type in the tree. So by default it's int, but you can use other type. You can use long or even more complicated types. And another thing is what is the function that we want for the tree to compute. So by default is max, but you can change this to min to a plus b for sum and or any other function you want to compute. So the only requirement is that it should be associative. And also there's a base value unit. So essentially this is a value when you have an empty range. So you want this unit operate with any of your actual value will result in that value. So for sum, this unit should be 0. For max, this should be the smallest, the lowest possible value. So maybe the int min. Yeah, and for min, this should be the maximum possible value. So essentially the base value. And also on the next slides, we have the code for update. So there, the default code is you replace the element with the value, and this will update. But sometimes you actually want to increment. You want to add 1 to that value. So just make sure that when you use the code, make sure that it does what you want to do. So I think here there's not much. The data is stored in this vector. So this slide has the main code. So the constructor given size n and also take the unit size. So I might have made some minor changes from the code I took from KACTL to make it a little bit less error prone. So basically, it forces you to provide the base value so that it's unlikely that you'll forget what value it is. It's unlikely you forget to specify the value, and then you get bugs that are difficult to debug. So this just initialize the variables in this class. So create the array of size 2n, and then assign n to the class variable n, and then assign the base value unit. And when you update, you provide the position you want to update and also the new value. So this is here, this assignment. So this equal means assign. If you want to do increment, this will be plus equal. And the base values in the leaves in the segment tree are stored in the second half. So the value actually stored is plus n. And then we need to update all the parents. So then by reaching all the parents, we just keep dividing by 2 from the leaves index. And every time the parent value will be computed based on the 2 children's value. So we're going from leaf all the way up, update all the nodes on the path. And then here is the code for query a range. So in this particular code, the left is closed, the right is open. And yeah, so it's just this one loop. I'm going to use the example on the next slide to illustrate how this range thing works. But essentially, so we start from the leaves. So we add n to both the beginning and the index so that we start at the leaves. And then we keep going while the beginning index is less than e. When they are equal, then we're done. And inside each loop, anytime b or e is odd, we need to add some other value. So we need to, if it's odd, then that's handled at this level. So we directly take that value into here. And then we increment b. Then the b will become even afterward. So So basically, if we have an odd, then that means we have a single element on that level that we have to take. So we do that. So this RA will keep track of all the value from the left side, and RB keep track of all the value from the right side. And when it stops, we will just return these two values added together. So let's think of this as sum. So then it just keep adding things. So here's a example illustrating a segment tree with 9 leaf nodes. So I want to choose a number that's not power of 2 to illustrate it actually works in those cases. So the elements stored in the array are actually from 9 to 17. So and all the previous nodes are used as internal nodes in the segment tree. And when we start, if our query range is from 0 to 7, and 7 is not included, so that's include the 7 element index at 0, 1, up to 6. So it's actually these 7 elements. So these yellow highlighted here are the 7 elements. In the initialization, we will add n to both beginning and end. So when we start, we add 9 to this. So the B and E value are 9 and 16. So because 9 is odd, so then we will directly add that value to the sum. Here, keep tracking in this RA. And then we will add 1 to B. B becomes 10. So 10 and 16 in the loop, we will divide both by 2. They become 5 and 8. So then we will be looking at node from 5 to 8. So then at this point, because 5 is again odd, so we will directly add what the value in 5 into the sum, and then we will increment this from 5 to 6. So then, because the node 5 is the parent of 10 and 11, so that means the 10 and 11 are also added. So 9 is added, 10 and 11 are added. And B is 4 and 8, they divided by 2, we get 3 and 4. So we'll be looking at nodes 3 and 4. Because 3 is odd, so we will add the value 3, the value in the node 3 to the value. And 3 represent the sum of 6 and 7, which represent the sum of basically 12 to 15. So by adding 3, we are adding 12 to 15 here. And then after we do that, we add 1 to B, so B equals E. I guess actually this actually shouldn't happen in that the B and E actually never go to 2 because they are equal. Then the loop simply stops. So what we have been added to the result is 9, 10, 11, 12, 13, 14, 15. So that's why this query works. So that's it. Next, we'll be looking at the